EX73. So before we state the main part of the exercise today, so let's put a result here, which we don't give a proof, but it's useful to solve our exercise because the proof is quite complicated. So let me just state it here. It's theorem again. So let M1, M2, MK, N all be R modules. R is commutative ring with multiplicative identity, the unitary. As before, suppose it's k bigger than 2, and suppose this is theorem 5.6 in Keith Conard's lecture notes. Suppose M1 product MK minus 2, MK minus 1, so we're not requiring this to be multilinear, just formally construct a map. The condition is that we require it to be bilinear in the position MK minus 1 and MK when the other coordinates are fixed. So we know that when you have a bilinear, you fix one position, it becomes a linear, right? As you could imagine, if you have a trilinear, you fix one position, it becomes bilinear. But here we don't require it to be a multilinear. We just say, okay, we have such a function, and we only know that it's bilinear on 2 positions, when other positions are fixed. Then, because you could still imagine this could have some relation with the tensor product of this 2 position that's a bilinear. So the conclusion is, responding our intuition, there is a unique function at one product. Again, sorry, product minus 2 product. So here comes the tensor product. The bilinear, our bilinear position, we got really a tensor. And this one is linear in this restricted part when the other coordinates are fixed. And satisfies what? Satisfies it has the same image as before. Evaluating on whatever arbitrary element. So on this tensor product, it becomes MK minus 1 tensor MK. But the image is the same as before. We just use this small part of the tensor product to say it very economically that that part is bilinear. Last remark, if this phi at the beginning is multilinear, on all positions, then this new constructed map phi, big phi, is multilinear in all positions. So don't give a proof of this. So let's use this to do our main part today's related with. But following, still you can see this as continue. Exercise 72. Still talking about the relation between Hom and tensor. Okay. So the main part of the exercise today is to prove the following thing. For R modules, big M and N, there is linear map from M due tensor N over R to the Hom factor from M to N. This is already something new, right? Sending each elementary tensor. Let's say phi tensor is small n. In the left hand side to a linear map on the right hand side. So let's give the construction to the linear map of course our linear map from M to N is defined by M is mapped to, still use the notation phi tensor N for that one. For its image, okay, and it's defined to be, as you could say, so M, if you apply phi on M, because it's M due is for into R, and so use the R module structure, but I could apply it on N. We claim that, or the exercise asks you to prove, this is an isomorphism. If this is an isomorphism, if there's some condition on M and N, and we'll give counterexamples. If M and N are both finite free, R modules, which means free R modules of finite rank. In particular, if F is a finite free R module, then we take M n equals N equals F. We would have F due tensor over R F isomorphic to Hom R F to F, which means endomorphism ring of F, right? So this is isomorphism as R modules again. Okay, this is the main part of the exercise we want to prove. So it looks like, so let me write it more clearly. So this is asking you to prove that if you have R linear map from M to R and tensor with N, this is isomorphism to R linear maps from M to N. This is not yet base extension, right? This is, I'm not tensor R with some ring S. If there is a ring homomorphism from R to S, no. Just tensor with R module. This is the claimed one. So let's say the solution. This is It's quite a long proof. So notice that start from the left hand side to the right hand side. The function from M due product with M and the product with N, then give N defined by, you have R in your map, you have element of M, you have element of N, they use this phi M, give R, and the action N is trilinear. So it's easy to check, okay? Because in each position, this is R linear. Phi is R linear map, and so phi itself has an R module structure. N is R module, and so all those tells you that this just described map is a trilinear map. Hence, by this first part of our exercise today, this map gives, this trilinear map gives a bilinear map. When you combine, or when you simplify two position, we have to write it as tensor product. Let's say I'm due tensor is N over R, and then product with M. This is totally symmetry in the first trilinear map. You could put whatever position as you want, order as you want. So I'm going to combine the first and the third one, combine it into a tensor product. Gives a bilinear map. This map is, as the first part exercise tells, have the same image as before, so it's again phi M N. And it tells you that if at the beginning it is multilinear, then after you reduce it to such a form, it is still multilinear, which means here it is still bilinear, right? This is bilinear. And so because this is bilinear, so for any element, let's take from here, this BT is still linear, and so this is linear from M to N, right? Now we have constructed such a map, right? We have already constructed this map. So we start with element. T here, and then give me N. I've constructed this. BT evaluate at N, which is BTN. Yeah, the construction is already given at the beginning. It's described in here. Okay. We just rewrite this using a bilinear map instead of a trilinear one. Now let M and N be finite Fourier modules. Suppose they're non-zero. Otherwise, the statement is trivial. And we want to show F is isomorphic. So let's call this let's call this F. Okay. So we first fix the basis for M and N. Then F mix the due of EJ, so due of EJ is in M. Due F mix due of EJ tensor with EI prime. So this is in M due tensor with N. Acts on N because whatever map F of element e.g. due tensor EI prime should in the R linear map from M to N. By sending each basis, you only have to define sectional basis, each EK to what? To EJ due, evaluate on EK. So this is in the M due, this is in M, so altogether this is already in R. And then you multiply with EI prime, so this is in N. Right. So summarize this F EJ due tensor EI prime. This is our linear map from M to N. I'm justifying its image on basis and extend linearly. Sends EJ to EI prime and others to 0. Else to 0. You can already see this kind of going to give you a basis. A basis for the R and for the R module home from M to N, right? Writing elements of M and N as coordinates under the fixed basis then these elements of this are linear map from M to N becomes matrices, and the image of just constructed e.g. dual tensor with EI prime become a matrix among those matrices, and we could describe it more clearly. It has only one let's just write it simply. It's only one on the ith row jth column, and then all elsewhere is totally zero. Obviously, such kind of matrices with ij choosing arbitrarily or run over all possible choices form a basis for all matrices. And so as a conclusion, so the image of F contains a basis of this free R module from M to N. It's very similar as linear vector spaces. You fix the basis and then the linear transformations become a vector space. Right, dimension is just the dimension of M times dimension of N, because it describes all elements by matrices and by N. The dimension of M times dimension of N. F is a linear map so this is out. Then we show that F is injective actually I put a question. If this is already, this is a free R module and you got our linear map, if it's already surjective, then it should be automatically injective, right? Let's go more constructive proof to show this is injective. Suppose our arbitrary element written under the fixed basis, let's say under the fixed basis, e.g. du EI prime. It has coordinates Cij as elements of, so this is in M du tensor N as a free module. Suppose this is 0. So this is 0 in as our linear map from M to N. Then evaluate both sides to some basis element, let's say EK. What do we have? On the right hand side is 0, on the left hand side, what do we have? Recall. This is EJ dual acting on EK and then dot with EI. Right, and so on the left hand side it should left only with say IK EI prime, and the right hand side is 0. And this implies hence say IK is 0 and for arbitrary K and for arbitrary I. This implies at the beginning the element was 0, so F is injective. Let's finish the next remark. First remark. Let's find an inverse of F directly. Let's start from the right hand side. And then let's define a map. Give me basis element of M, so this is inside M. I give you back element in N. So I'm just defining what is EIJ actually using the factor R. L is already. I'm not yet constructed element on the left hand side, right? So I'm using matrix to represent L. With respect to the chosen basis. Now we write L equals the image under F of some element. So to construct the inverse is to just to decide the CIJ using L, right? So to be determined. Suppose this is the case, then at least we know we just let's see what happens if this is the case. We want to sometimes reverse the direction. So this will give EJ due on EK and EI prime. This is our definition. Again, this would be just say IK for all the I. Because J must equals K to be able to be non-zero, EI prime. So the conclusion is say IK equals AIK. Because L the beginning, it is defined using AIK. For all I and K, or if you want to write it more tidily, I and J, same thing. And so the conclusion is L are linear map from M to N with matrix representation Aij corresponds to the tensor Aij Ej due tensor Ei prime in M due tensor N. This is a direct proof. So we constructed the inverse map. The L whose matrix is Aij map to Aij Ej due Ei prime. This now third part of the exercise, counterexample. If M and N are not finite free R module, then in general we don't have the due of M tensor N isomorphic to Hom of M to N. I think, let's say if you have our linear map here, you have element N, you can still say give me element M, I map it to phi of M acting on N. This is still our linear. You have such map, but it will not be isomorphism. So the counterexample is take R to be sigma p squared, take M and N to be pz quotient p squared as submodule of R. Now small exercise 3.1. Check that M due is isomorphic to M. 3.2. Check that M tensor product self tensor product isomorphic to itself. Sub exercise 3.3. Check that our linear map from M to M is isomorphic to M. And last sub exercise, check that the same construction as in main exercise, the second part of the exercise today, which is this one. If M is finite free R modular, this is isomorphism, but check that this is the identically zero map. And so this give you a counterexample after you finish all the sub exercise. Okay, let's start from 3.1. So you have pz modulo p square, map it to z modulo p square as z modulo p square module. So how can you do that? It's uniquely determined by the image of identity. So this is order p. So basically you can only map it to whatever other p elements here. The other p elements are those killed by p, so it's, you must map it to something here, right? And you can choose whatever elements here. This is isomorphic to pz. Well, p square is isomorphic to itself. 3.2. So you have pz p square, pz p square, bilinear map. So the bilinear map, let's say for any element of the form px bar, py bar, because elements here you can always, it's in the submodule or in the ideal generated by p, so you can always write it uniquely as not necessarily uniquely, because after quotient you choose whatever representative, you can always write it in the form px bar py bar, and I map it to, I'm not going to map it to p square xy because that would be 0. I'm going to map it to pxy bar, and you check this is z quotient p square bilinear, because x and y only contribute to the term on the right hand side linearly, right? And so this gives you rise to this M tensor with M to M, and this is again px py map to, sorry, px tensor py map to pxy. And then let's check its surjective. Obviously, y is injective. So notice this could be rewrite as p tensor xy bar. And so if pxy bar is 0, this implies at the beginning it's 0. And so this is injective. Okay, 3.3. Prove that the whole map from M to M itself is isomorphic to M, our linear map. Our linear map from pz p squared to z p squared. I mean, yes, so this is inside R, but as we said, actually you could only map element to those has order p, but it's still M itself. So the same argument, you could choose whatever element here. Now the last one to say that the map we just constructed as in exercise 2 of today tells us that the map we construct tells us that we're going to map from here to here. The map is sending a phi and an n, and then map it to the map which maps it to phi m, and then why this is 0, we have to show that, right? This is because phi of m, as we have showed, phi of m is always fall into the p torsion parts. So phi of m by our construction is not only in R but in M, which is pz quotient p square. This R is z quotient p square. So this is already in pz quotient p square. And then you multiply with n here n is the same as m in our case, which is p is equal to p squared. So p is equal to p squared times p is equal to p squared is 0. And so we are done.